Okay, so you might wonder, what is the point of all this? Okay, the cool thing about redox reactions is they actually have applications in something you deal with every single day. And what you have is you have electrons being transferred. Well, moving electrons is electric current. And this is where kind of the idea behind batteries come from. So if you have a battery, like a AA battery in your calculator, or you have a battery in your cell phone, that's the idea. What those batteries are made out of is chemical redox reactions that transfer electrons, and it's been turned into a useful way of producing electricity. That's what it is. So, for example, I've done this demo for you guys in the past. Copper 2+, this comes from CuCl2, but again, chloride is a spectator, and Al, tinfoil, or actually aluminum foil, turns into AlCl3 and solid copper. That is a redox reaction. And if you just dump them together, these are the half reactions that take place. The Cu2+ gets reduced, gains electrons. The Al3+, or the Al gets oxidized, loses those electrons. And if you put them in the same jar, reaction happens. It happens without doing anything useful. It's called a spontaneous reaction. It just happens. But if you separate it properly, then you can use those electrons to do work, to create a battery, to produce electricity. And this is one way of creating batteries. Not the only way, but it's one way. And the way a battery is set up is it's this thing's called the galvanic cells. And I will have a demo for you guys where you can see what they look like. Basically what you have is you have a beaker, and you have chunks of metal, and they have two different parts to it there, and it's called half cells, kind of like we did the half reactions. It's a half cell. One part of it is called the anode, and the anode is wherever you have oxidation taking place, and you have the cathode, and the cathode is where reduction takes place. Okay, so based on our previous reaction that we had, the electrodes are usually chunks of solid metal sitting in a solution of like ions, meaning the same element, okay, except they're ionic. So, for example, in our previous one, what we had is we had Cu2+ plus 2 electrons turning into solid Cu. Okay, that's being reduced. And inside here I would have Cu2+. It would probably be a blue solution. And I would have a chunk of copper sitting right there. Over here, in the oxidation, I have aluminum solid changing into aluminum 3+ plus 3 electrons. And so my aluminum 3+ is sitting in solution. And then I have chunks of the metal sitting there. And that's how you set up a galvanic cell. And what happens is the electrons travel through those wires that connect them. And that's how you get a battery. As the electrons travel, they always travel from the anode to the cathode, A to C, because the anode is oxidized and it is losing electrons. The cathode is reduced and therefore it is gaining the electrons. So the electrons have to go from anode to cathode. Doesn't have to be on the right side and the left side. They always go from the anode to the cathode. If the anode was over on this side and the cathode was on that side, the electrons would go the other way. Electrons always travel from the anode to the cathode. So if I set this up, the reaction will start. The electrons are going to start to travel, but it's going to stop almost immediately. Okay? Because what happens inside here is I have solid aluminum with a charge of 0 turning into Al3+. And so the positive charge is increasing inside the container because I'm making Al3+. On this half of it, I have Cu2+ turning into Cu0, and the positive charge is decreasing inside the container. Now, if you think about it, it kind of makes sense. Electrons are negative. Why are they going to want to go someplace where it's becoming less positive? They're going to want to stay where the positive charge is increasing. And so it stops because you build up this charge. You increase the positive charge on one side and you decrease it on the other. And it just stops. So you have to have something to kind of counterbalance that. And what they create is this thing called a salt bridge. It allows the current to flow and charge doesn't build up. And what a salt bridge contains is typically a spectator ion. It could be potassium and nitrate. Those are probably the most common ones. It could be sodium and chloride. Okay, but the idea is it helps balance the charge. So if you remember, I said this is going from a charge of 0 to positive 3, so the positive charge is increasing. Well, these negative anions are going to slide through my bridge, and the negative ions are going to balance that increase positive charge. Over here, I have Cu2 plus turning into Cu, so the positive charge is decreasing. So over here, my positive ions balance the decreasing positive charge. And what that does is it allows the electrons to travel from the anode to cathode because the charge remains balanced. Now, I have rarely gotten salt bridges to work, as in rarely gotten salt bridges to work. However, there is another way of doing it, and we'll talk about that when I do the demo. Hopefully when you guys do the lab it works. So now, how much electricity can we get out of it? Well, that's called cell potential. Cell meaning not like the cells of your body, chemical cells, galvanic cells, batteries, potential for batteries. And the push or pull of the electrons between the anode and the cathode is called the cell potential. Remember, anode is pushing them away because it's producing them. The cathode is pulling them towards themselves, and it's called the cell potential. It's also referred to as electromotive force. The unit it has is the volt. So if you've ever looked at a AA battery, I think it's 1.5 volts. You've probably seen a 9-volt battery before. That's what it is. It's how much pushing and pulling between the electrons from one side to the other happen. And the more that they push or pull away, what you get is you get a higher voltage, a higher potential for the cell. It's measured with a voltmeter. You guys are going to do that in class. But we have to have something to compare it to. So what they're going to do is, instead of having my chunk of copper or my chunk of aluminum, they're going to compare it to something called the standard hydrogen electrode. That's the comparison they're all going to use. All other oxidations are compared to that. This is considered to be 0. Everything else is in reference to that. And there is this little 0 here. It means it's standard state, 25 degrees, 1 atmosphere, 1 molar solutions. Doesn't really apply to you guys. That's more of an AP level thing. So, how do we calculate cell potential? Okay, somewhere in your homework packet, you will see a table. It's called Standard Reduction Potentials in Aqueous Solution at 25 degrees C. It's called an SRP table. Okay, and it's based off of that. The total cell potential is the sum of the potential at each electrode. So, what I want you guys to do is take a minute and see if you can find this one in that homework packet. Be careful, because there's a lot of coppers. Okay, there's 3 different versions of this, so you want to be real careful. Cu2 plus going to Cu with a charge of 0. So if you look on that, it's about 1/3 of the way down, and it says positive 0.34 units are volts. Okay, now I want you to look for this one, and it's interesting because you're not going to see it written like that. You're going to see it written a different way. That's about 1/3 of the way up from the bottom, maybe even 1/4 away from up from the bottom. In there, it's written as Al3 plus goes to Al. And the reason for that is because that is a reduction potential. And so what you need to do is take that number. This was negative 1.66. That means this one is positive 1.66. And to find the cell potential, I'm going to erase the ink. This was 1.66. This is 0.34. Add them together to get the total voltage, 2 volts. And a spontaneous galvanic cell has a positive cell potential. Okay, if it's negative, it's not spontaneous. It's a dead battery, if you will. You can look up reduction potentials in a table. Remember, they're all reductions. If you look for this one, it's going to be written like this. Al3 plus goes to Al. That is a reduction. So one of the reactions have to be reversed to turn it into oxidation. And that what you do is you change its sign. That's all you do. You don't multiply by the 2 or the 3. All you do is change the sign and add them together. So, I'm going to have you guys practice. I want you guys to look these up. what you have is you have Cr3 plus goes to Cr, and you have Pb goes to Pb2 plus. Now keep in mind the electrons aren't written here, but if you wanted to, you would write 3 electrons here, balances the charge to 0, and 2 electrons here. This one is being reduced. This one is being oxidized. Okay, so if you look up the Cr3 plus, that is middle-ish, middle bottom-ish. It's negative 0.74 volts. And then you look up the lead, and again, this is oxidized. So what you're going to find on the chart is the reverse version. Pb2 plus 2 electrons goes to Pb. That is about in the middle. That's negative 0.13 volts. That means this one is positive 0.13 volts. Sum total 0.61, negative 0.61 volts. So this is not a spontaneous reaction. It's not going to happen. It's a dead battery. And I'm going to erase the ink. All right, so you have Au going to Au3 plus, H1 plus going to H2. This one's in the middle. That one is 0. If you want, you can put a 2 here and put in the 2 electrons. That's the balanced redox reaction. It is being reduced. If you look up gold, remember, it's being oxidized here, so you're going to look up the number. It's going to be negative 1.50 because Au3 plus as a reduction is positive 1.50. Add those together, negative 1.50 volts total. Again, not a spontaneous reaction. Now this is an interesting one, okay? Because the cell potential is negative, what that means is this reaction doesn't happen. I want you to look at the reaction. Gold, H plus, that would be acid. That means I could take my gold wedding ring, right, I've had it a long time, and I could dump it into the nastiest acid I have, 18 molarity sulfuric acid, and nothing will happen because the cell potential is negative. It will not react. Now, I could put it on my clothes, it will eat my clothes up. I could put it with a piece of metal other than gold, it will probably eat that metal up. But gold is very valuable because gold likes to be reduced. It does not like to be oxidized. That's why you can dig it up out of the ground, is because it doesn't react with anything. It's just the nature of gold. That's why gold's valuable. You don't have to do anything to generate the metal. Aluminum, you can't dig aluminum up out of the ground. Zinc, you can't dig that up out of the ground. They all get oxidized. They all react with all kinds of stuff. And as a result, you have to put a lot of effort in to get those metals out. But gold, silver, copper prefer to be reduced. They like to exist as the element. And so that's what makes them valuable. That's why they're coins. All right, let's look at this one. Cu goes to Cu2 plus. Cr3 plus goes to Cr. And again, I'm putting in the electrons. Not necessary to figure out the potential, but sometimes it helps to find things. Negative 0.74 volts. And again, this is being oxidized, so when I find that one, I'm going to change the sign on it. Negative 0.34 volts. Add them together. Negative 1.08 volts. Again, doesn't happen. Copper likes to remain as an element. It doesn't like to be oxidized. Okay. So now I'm just going to show you this one. So write the spontaneous equation. We're not going to do that part because we haven't done balancing yet. But I want you to calculate the cell potential for a galvanic cell based on the following half reactions. Now if you notice, they're both gaining electrons, reduced and reduced. One of them has to be oxidized. And in order to be spontaneous, okay, that means the cell potential, when I add those numbers together, has to be greater than 0. So one of them has to turn around. Well, I think it's pretty obvious that this one, if I turn it around, Mg goes to Mg2 plus 2 electrons is positive 2.37 volts. I add it together with that, I get positive 0.71 volts. Actually, this is where our activity series comes from, is from cell potentials. Okay, metals like magnesium are very, very reactive. They have a high activity, and as a result, It's because they form a positive cell, a positive reaction, a spontaneous reaction if you want.